Redundancy in distribution network. So many distribution networks are of meshed in structure, but they will operate in radial form. So this allows for interruption to be limited in the duration by means of some switching action. To ensure that a backup operation is, the network should also not in case to be overloaded. Consider an example shown here in the below figure. So before actually jumping into this topic, there are some few certain equations that needs to be recap from our previous sessions. So here the generation loading and the generation being a sum of the two feeders. Here we need to consider that P generation comma 1 plus P generation comma 2 maximum should be always less than P consumption 1 plus P consumption 2 maximum plus P consumption 1 and P consumption 2 minimum. So during normal operation, the following relation that holds good. Here you can see that the following relations. The P generation 1 maximum should be less than P consumption 1 maximum plus P consumption 1 minimum. So P generation 2 is also same, the P consumption 2 maximum plus P consumption 2 minimum. So in theory, situation could occur where the condition above from the above equations are fulfilled, but the conditions are not fulfilled in P generation 1 equations. The load maximum could occur where there is a difference in the instant of time. So this is given by, so that the P constant 1 plus P constant 2 maximum should be always less than P constant 1 maximum plus P constant 2 maximum, where the load minimum and generation maximum could occur at the same time. Although in the theory it is possible where it should be further noted that which gives only a first hosting capacity, behind which the risk becomes a overload higher than the network without distribution generation. So second hosting capacity behind which the risk becomes overload is unacceptable here. Extreme cases might still occur, mainly when large units are connected towards the end of the feeder. There are a number of solutions are available here for coping up this situation. So among these few are like limiting the generator size, so enforcing our distribution network, and accept the backup operation where it is not possible in almost all the cases, and the curtailment of generation during backup. So all these are some of the solution to cope up our redundancy in the distributed network. So latter it is most reasonable solution where the curtailment is needed only for duration of period within high production or low consumption, and when at the same time the feeder is not available here, the probability of this will be very small. The main cost will be more in detail or instructions that has to be followed by our distribution network operator to prevent this overloading, and also during backup operation as well. A more advanced solutions could be considered where hosting capacity is calculated after every switching action. The production from distribution to generation is curtailed once it exceeds the hosting capacity for actual operation states of this distribution system. In either case, there will be no limit on installed capacity, but only there will be an actual production of power. So this is about the redundancy in distribution network. So moving on to the meshed operation. Here the transmission and the distribution networks are operated on a mesh so that the losses of the components does not result in interruption for many customers. The meshed operation has some potential impact for risk of this overloading. So in the radial network, distributed generation will always result in the reduction in the network loading as long as the amount of this distributed generation is less than the first hosting capacity. So whenever this network operated in a mesh, there will be no longer such case exist. An example for this is a figure which is shown. Consider this figure. I will show. Consider this figure is shown here. So a large power flow takes place between A, B and C. Here, so whenever this large power flow takes place between two regions, consider two regions which are interconnected in a network, the result is a large power flow in the connection between A and B, as well as there is a less power flow in the loop. So here ACDB is one of the loop. So there will be less power flow in this loop, which is indicated by that dotted line ACDB. The load connected to the bus C will increase the flow of the connection from A to C, but same time which reduces the flow from D to B. So adding distributed generator at node C initially, which will result in the reduction of load, and thus there will be increase in the power flow between that dB. Adding this distributed generation at n C will significantly increase the power flow between that D and B. Already small amount of generation which may result in some overloading can be prevented by doing so. But a situation like this are not likely to occur due to small size distributed generation. The reduction in loading will occur for all the buses in the similar way. The concern is, however, especially with the connection of this larger wind park, the subtransmission network, and long distance power transfer could result in the parallel power flow through the subtransmission network. The connection of small amount of this generation could also cause this overload. So very small capacity value could result in all possible operation state, which has to be considered. Here consider a network shown. So it is a linearized DC which is used to obtain an expression for a power flow through C and D due to large power transfer through this region. Neglecting some resistance, the active power transferred over a line is a function of this angular difference and between the voltage on both the side of our line. So here Pij is equals to sin theta ij divided by Zij, where Zij is the impedance of our line. For linearization of this following expression, Pij can be also written as sin ij divided by Zij. For the connection for C and D, it can be written as PCD. In general, PCD is equals to theta CD divided by ZCD, where ZCD is the impedance of that CD line. For other connections, similar expressions are obtained when it has been used to flow that AC is the sum of flows through CD and a load at a bus C. And the flow through dB is a difference between the flow through CD and the load at a bus D. Here the power flow through CD and the load bus C, if I product that both two, I will get the following equation, that is PCD plus PC is equals to theta AC divided by ZAC. ZAC is the impedance of the line AC. So if I product that, I will get impedance power flow or impedance of this dB line. So PCD minus PD will gives me theta dB divided by Z dB. So whenever I consider the power flow alone through AB, it gives the following expression that PAB is equals to theta AB divided by ZAB. So if I combine the above two equation, that is theta AB is equals to theta CD plus theta dB, the following relation is obtained through the power flow through AB. So the power flow through AB is given by ZCD plus ZAC plus ZB into the product of power flow through CD plus the impedance of AC line plus power flow through C, that is where our the load has been connected, to the difference of impedance of the line BD and the power flow through the line D. So which is divided by the total impedance of the line AB. This is the overall expression for meshed network, power flow through AB. Moving on, we'll see some redundancy in meshed network. In transmission and sub-transmission network, the planning and operations are based on the principle N-1 principle. Under this principle, the losses of the single component could not lead an interruption for any other customers. The detail of this principle and difference in the application between transmission and sub-transmission will vary between network operators to network operators. Here a simple example is shown. Consider this figure. Where 50 megawatt load is supplied through a double circuit line with a capacity equal to 60 megawatt per circuit. When minimum load is 20 megawatt up to 140 megawatt, that is 120 plus 20 megawatts of generation can be connected. So without overloading our line, we can connect 120 to 120 plus 20 megawatts of line. However, so N-1 principle is applied to the hosting capacity only for 80 megawatt. That is, we split up at 80 megawatt as a 60 plus 20. So here N-1 principle requires that losses of any component does not result in the interruption of any of our consumers. So this principle is used as a operational principle by almost all the transmission system operators. At sub-transmission level, the principle is strictly applied during the operation, although the details differs between the operators to operators. So one of the important point that has gone in the discussion in this module is about that N-1 principle, which is used to during designing of our networks. Design criteria is to be something like for operational state, and the loss of component should not result in any overload or anywhere in our network. So most of the network operators do not perform calculations for operational states and for all the component losses. Instead, a limited number of operational states are considered, typically which includes maximum demand, minimum demand. Prior knowledge about this critical operation states is needed for these operations. For each operational state, either single contingency where the loss of one component or a predetermined list with most severe contingencies has to be studied. The calculations are repeated for increasing the amount of generation until one or more network elements become overload. The highest amount of generation will not result in any overload in the hosting capacity. A solution that allows more generation to be connected while still making n-1 principal is to use so-called interrupt scheme. The interrupt schemes ensure that a certain breaker is opened once and after that another breaker will open. In most common application with distance protection of these overhead lines, the speed up of opening of breaker is further away from the fault, has to operate immediately. The interrupt scheme of this would be shown in the figure that consider that second figure for the interrupt scheme. So the trip G breaker, so whenever one of the breakers in A, B, C, D is tripped, so the trip at a G will trip. So this is again contingency which is experienced with our network operators. In this way, the whole transport capacity of double circuit line can be used, but without risking the overhead when one or the two lines trips. The inter-trip scheme allows in this case to connect up to 140 megawatt of generation instead of 80 megawatts. The drawback is here is the generation or the part of generation. So it is tripped whenever one of the lines is tripped. So this is how which limits the amount of time where the maintenance comes into an act. The choice of operational state and contingency is mainly based on experience by our network operators. Most of the severe operational states and the most severe contingencies should be chosen in such a way that the operation of existing system that without distribution generation, with a large amount of distribution generation, different operational state and different contingencies may become one of the cause that high for an high component loading. It is also therefore recommended to take as many operational state contingencies that is in practical. Some pre-considerations are also recommended for this operational state and contingencies that may result in high component loading. Here a simplified network is shown. That's here you can see that simplified network. Some pre-considerations are also recommended on this operational state and contingencies. Here thermal loadability of the connections are indicated. The range of the load buses are C and D. We assume that n-1 principle is used to determine the maximum amount of generation that could be connected. A 30 megawatt of capacity connection, that is C and D, will limit the amount of generation at a buses C and D. During this loss of connection, A and C and the minimum load at a bus C are more than 40 megawatts of generation that can be connected at bus C. During this loss of connection BD, whenever there is a loss in the connection between the bus BD, the amount of generation at a bus D is limited to 35 megawatt. The total amount of generation is limited by the capacity of connection A and C and B and D, which is not more than 65 megawatt. So again here the split up is shown as a 50 plus 10 plus 10. The hosting capacity for the source of generation could be smaller than this for a number of reasons. Among that we identified only two such reasons. Due to the presence of existing hydropower, which may included in our hosting capacity, and consider a 30 megawatt hydropower generator already connected to the bus C. The hosting capacity for this new generation, for example in our wind park, in that case only 10 megawatt for the bus C and 35 megawatt for the bus C and D together. The presence of this parallel flow could become a limiting factor. When A and B is a single connection, the transported power through the region can never be more than 30 megawatts. A more likely situation that is between A and B is a double circuit line or a corridor with a number of lines in the parallel. The loss of one circuit could increase the power flow through C and D. The maximum amount of power that can be transported through the region is 30 megawatts of power, that is from C to D after the losses. So the total power is given by the power that is transferred from A to B is given by the following equation. That is PAB is equals to ZCD plus ZAC plus ZBD. These are the impedance of all the three consecutive lines, and ZAB is the impedance of the line AB, and power flow through CD is represented by PCD plus ZAC divided by ZAB into the product of PC minus the ratio of that ZBD and ZAB to the product of power flow through T. With the PCD, the maximum permitted power through CD and PC and PD are the loading for the consumption and minus the generation at the node C and D respectively. ZAB, the highest value of impedance between AB after the loss of one circuit. Adding generation to the bus C will reduce PC and thus the reduced significant amount of power that could be transported through this region. A larger value of ZAC will due to the longer line AC and more transfer capacity impacted by the generation connected to the bus C. When large power transfer through this region are common, the hosting capacity could be very small or even sometimes zero. In case of large power transfer in both the direction, the hosting capacity for new generation at a bus D might be equally small. Also in this case, the inter-trip scheme might be able to result in higher hosting capacity. One possibility is to trip the connection AC when one of the circuit between AB is tripped. The network become here radial and loop for the power flows which are not longer possible. Alternatively, the generation or the part of generation at a bus C might be tripped. So inter-trip scheme uses a simple logic. Reduction in the generation is enough. The modern production and communication technology allows more subtle solution for this. So here the generation connected to bus C could here one more solution can be possible in the inter-trip scheme. So consider this figure. Here the generation connected to bus C could limits the power flow through C and D, which remains the flow of connection between C and D as an our input parameter. So with multiple generators feeding to the same bus or nearby during a larger power flow region, in such condition, the hosting capacity which we are discussed in our previous slide, the hosting capacity could be even small or even sometimes zero whenever this n-1 principle has to be fulfilled. The network is reproduced in the second figure. What you are seeing, it is of network that is reproduced. Here the majority of power flow between A and B, but some amount of power will also flows through that C and D. Upon the loss of one connection between A and B, the connection between C and D will become overloaded. Adding generation at bus C will increase some amount of power flow between the C and D. For same flow between A and B, when the transport capacity of C and D is a limiting factor, the presence of this generation at bus C will reduce some amount of power that could be transported through this region. That is why we are adding some generator at C. Inter-trip scheme will trip the generator when one of our 4 breaker in any one of our 4 breakers will trip off. In such condition, the A and B will be opened. In this way, n-1 principle is still it is fulfilled with same time with a larger amount of generation can be connected. So this is about redundancy in meshed network and so meshed operation, and we have seen redundancy in distributed network also. Moving on, as a last we will see the losses. So here estimating the increase in the or decrease in the losses are due to this introduction of distributed network, which may require more detailed studies than estimating. So an increase in the losses can be compensated by the reduction of another movement or the movement in time or another location. So what matters here is the total losses over all the feeder sections and which are integrated over time. So this is about last session of our module 2. So far we have covered the losses, redundancy in mesh network, radial network, and redundancy in meshed operations and all we have seen.